Students, are you able to see the PPT?
Yes, sir.
Okay. Okay, so we were discussing about this frequency response of a BJT amplifier, and here we already discussed the effect of coupling capacitor, right? So we find that the dip in the voltage gain in the low frequency region is caused due to coupling capacitor. So here you can find the coupling capacitors like CC1 and CC2. And you can find another capacitor here, and we have given the name CE. And this is the bypass capacitor. So what is the effect of bypass capacitor on the frequency response? So that we will see now. Effect of bypass capacitor. Right. So bypass capacitor bypass capacitor is your CE, is connected in parallel to RE, right? So in parallel to RE resistance, we are having a capacitor that is your bypass capacitor, right? Now in low frequency, no, we are talking about first we will talk about mid frequency and high frequency region. In mid frequency, mid frequency or high frequency. Region. So here the frequency is higher than the low frequency region, right? So in that frequency region, the resistance or capacitive reactance, we can say the reactance offered by CE is very less. Right? So because see, already we know that XC is inversely proportional to 1 by F. Right? So now we are talking about high frequency and mid frequency. In mid frequency also frequency is higher. So in mid frequency and high frequency region, since the frequency is high, so the XC will be less, right? It will be very less. And it is considered as short circuit. It is considered as short circuit, right? So now if you see this figure, I will draw here figure. I am concentrating only on bypass capacitor, right? Like this. So here there is RE. Now in parallel we are having capacitor, right? Coupling capacitor. But at high frequency it acts as short circuit. It acts as short circuit. So here you can see your XC is 0. The capacitive reactance XCE, I write it XCE of CE capacitor is 0. So now if it is 0, so now you can see there is a short circuit path. So now you tell me whether there is a voltage drop across this parallel combination of RE and a short circuit path. Whether there is a voltage drop across RE and parallel short circuit path. See, whole current will pass through this short circuit path, right? No current will go towards the RE. So if whole current is passing through the short circuit, then what voltage drop you will get across the short circuit? What is the voltage drop across short circuit? Yeah, someone can respond.
Voltage is 0, sir.
So 0 drop, there is no voltage drop. So if there is no voltage drop, right? So here whatever you are taking output here, V out, whole voltage you will get across, you will get at the output, right? So in mid frequency or high frequency region, the reactance offered by CE is very less and it is considered as short circuit. And there is no voltage drop. No voltage drop across short circuit, right? So this bypass capacitor will not cause the voltage drop when the transistor is operating in high frequency region or mid frequency region, right? You just see here this frequency response. In mid frequency region it is flat, right? There is no voltage drop, okay. But now you see in high frequency region there is a voltage drop, is you can see the voltage gain is reducing. If voltage gain is reducing in the high frequency region, then whether it is due to the bypass capacitor, no, it is not due to the bypass capacitor, because at high frequency this bypass capacitor offers a short circuit path. So there is no voltage drop. If there is no voltage drop across that, then you will get full voltage gain. So this drop is there. So this drop is not due to bypass capacitor. This is point number one. And already we have seen that this drop is also not due to coupling capacitor, right? So there is no drop. This drop is not due to the bypass capacitor. So here, so there is no voltage drop across short circuit, right? So here you can write this. The dip in voltage gain in high frequency region is not due to bypass capacitor. This is point number one. Y is not due to bypass, right? Now fourth point. In low frequency region, now you come to the low frequency region. Now frequency is low, it is very low, right? Now since the frequency is low, so the bypass capacitor will offer a resistance, right? It offers a resistance. So in low frequency region, bypass capacitor offers resistance or what's reactance, right? So it offers reactance. So this figure you can, I call it as okay, here this is my figure 1, right? This figure 1 is for this. So now it offers a resistance. So the figure will look like this. There is Re and there is some reactance offered due to capacitor. Let's see, this is XCE, right? So now here you are having a parallel combination of Re and XCE, which have some finite. If you solve it, then you will have some equivalent resistance value. So if the current will pass through that resistance, then there is a voltage drop, right? There is a, so if there is voltage Re and XCE parallel combination, then whatever final output you are getting, that output will also decrease, because whatever final output you are getting, some of that output is uh, is uh, you are getting across the parallel combination of Re and XCE. So the voltage gain will decrease, right? So this is for now, this is explanation is for your figure 2, right? This is your figure 2. So there is a equivalent resistance. There is a equivalent resistance of Re in parallel with XCE, right? So due to this equivalent resistance, what will happen? Therefore, there is a voltage drop.
Decrease.
Yes, there is a voltage drop across Re parallel to XCE, right? And now if there is a voltage drop across this, then therefore final V out, therefore final V out will decrease, right? And if final V out will decrease, then voltage gain will also decrease, because voltage gain is V out by V in, and V out is decreased, so your voltage gain will also decrease. Therefore, voltage gain decrease. Okay. So we have seen that the dip in the voltage gain, in the low frequency region is due to two components. One is coupling capacitors and second is bypass capacitors, right? So here we can conclude here one thing. The dip in voltage gain in low frequency region is due to coupling capacitors and bypass capacitors, right? Right. So this is first conclusion, and second conclusion is coupling and bypass capacitors do not affect voltage gain in high and mid frequency regions. Okay, so this we have come to this conclusion, right? Now just see here. Ideally, what we want? Ideally, we want that our voltage gain should remain constant throughout the entire operation of the amplifier. Whatever frequency we are applying for the amplification, the voltage gain should remain constant, right? But here what is happening at low frequency, we are finding that there is a decrement in the voltage gain, right? And that is due to the coupling capacitors and bypass capacitors. But we cannot remove those capacitors, right? If we remove those capacitors, then again there is a problem, because we are using those capacitors for isolating our circuit from the AC source, right? We want that whole input, whatever we want to amplify, it should enter to the transistor. For that we are using coupling capacitor, and this DC voltage should not come out from the transistor side. So we are using coupling capacitor. So we cannot ignore the coupling capacitors. So effect of the coupling capacitor is the decrement in the voltage gain, right? Now we will see whatever coupling capacitor and bypass capacitor we are having, those capacitors are responsible for this drop, right? So whatever voltage drop you are seeing here in this red color I am showing, it is due to the coupling and bypass capacitor. So now the question is, in this high frequency region, if we go, then here also we find there is drop in the voltage gain. So which is responsible for this drop? So that we will see. One thing we find out, in the low frequency region, the drop is due to coupling capacitors and bypass capacitors. But we have still not discussed the drop in the high frequency region is caused due to which particular parameter, right? Okay. So we shall go back to our basics, by which we started our this course. We started this course with PN junction diode, right? Do you remember? So in PN junction diode, if you see, suppose this is one PN junction diode. This is junction. This is P region. This is N region, right? And here, this is your depletion region, right? Can anyone tell me what is the meaning of depletion region? Yeah, can anyone tell me what is the meaning of depletion region? Yes, come on, fast. What is depletion region in a PN junction diode?
The region between P and N.
Region between P and N. What is the specialty in depletion region? Why it is called as depletion region? The question is, what is this depletion region? Why this region has been created, right? See, P material is up to this point, and N material is also up to here, this point, right? This is a junction. This is a junction here. But I am saying up to here and up to here, there is some region which is called as depletion region. I already told you, depletion region is that region in which there is no charge carriers, right? There is no charge carriers. Because see, if you remember, if you recall, then if suppose this is P and N material, this is P and this is N. This side we are having P materials, uh, uh, P impurities. This side we are having N impurity, right? And in P side you will find a small number of minority carriers, and in P N side you will find a small number of minority carriers, that is plus. So now In the initial classes, I discussed that due to the concentration gradient, what is the meaning of concentration gradient? The variation in the concentration. The charge will move from high concentration to low concentration. So see, in N type, you are having high concentration of N material. In P side, you are having low concentration of N type material, N type impurity, N type charge. So the charge will move from high concentration to low concentration, means this electron from N side, it will start moving towards P side. Same way it will happen in P side also. In P side, the majority carriers are positive charge. In N type, you will find less number of positive charge, which are minority carrier. So there is a concentration gradient. So positive charge, it start moving from P type to N type. And the negative charge will start moving from N type to P type. Why it is moving? Due to the concentration gradient. So now what will happen when N type and P type, they will cross each other, then N type will recombine with P type, and what will happen? This hole will disappear. This hole and this one electron will disappear. Now again this hole and this electron will disappear. This positive charge and this electron will disappear. So in this way you will find some region is created. This type, one region is created where there is no charge carrier, right? There is no charge carrier. So this region is called as depletion region. Okay. So in depletion region, there is no charge carrier. Now you think about a capacitor. What is the capacitor? There are two plates, right? There are two plates. Metal plates are there. So in these plates, this is your plate 1. And this is our plate 2. Right? And in between, what is there in between these two plates? In between these two plates, what type material is there? Yeah, can anyone tell?
Dielectric.
Yeah, dielectric means through which current will not pass, right? That is dielectric. So here you are having dielectric. Dielectric means where there is no charge carriers, right? Dielectric material. But in plate 1 and plate 2, there are charge carriers, right? Plate 1 and plate 2 are having the charge carrier because these plates are made up of metal. Suppose they are made up of metal. So metal, you will find free electrons. There are charge carriers. So there are two plates having charge carriers which are separated by a dielectric material, right? Now you see this PN junction diode. Here P side, you are having positive charge. Charge carriers are there, positive charge. In N side, you will find negative charge, right? Negative charge. In between these two charges, what is this region? This is depletion region. In depletion region, there is no charge. So you consider it as a dielectric, right? You consider it as a dielectric. So wherever you find a PN junction, you will always find a capacitance is there, right? If you recall, then we discussed about transition capacitance, right? We discussed about transition capacitance, storage capacitance. Do you remember? We discussed about these things in PN junction diode, storage capacitance, transition capacitance. So each PN junction, wherever you find a PN junction, there is always one capacitor, right? I will show you this transition and storage capacitor. It might be available in in the same PPT here. I will show you. It is saving the content. Okay, in Zener diode, this potential barrier, PN junction, I think it is not saved in this PPT, but it was there. We discussed about this. It is not saved in this PPT. Yeah, any student remember that we discussed regarding this?
Yes, sir.
Yes.
Space charge capacitance topic.
Yes. Yeah,
Yes.
space charge capacitance transition, that is also called as transition capacitance, right?
Yes, sir.
Okay. So see, now those capacitances are there, and those capacitances are now if you see a transistor, right? If you see a transistor, then the structure of transistor, if we will see like this, N, P, N. So here you will find one depletion region in this region, and at this junction you will find another depletion region. So you will find the capacitors here, right? You will find the capacitances are there, right? These capacitors, and these capacitors are the inherent property of the transistor, right? If you are having any transistor, NPN or PNP, whatever it may be, the internal capacitance will always be there. You cannot remove those capacitance, right? Because there is P material, there is N material, and there will be a depletion region, so there will be a capacitance, right? So now these capacitance will also play an important role when you are using a signal for the amplification, right? Because if capacitance is there, then it will have some reactance also, and that reactance will depend upon the frequency of the operation. So this is these are called as inherent capacitance, right? Because it is the internally it will be created. You have not connected any capacitor here. Intentionally you have not connected any capacitor, but due to the construction of the transistor, you will find internally these type of capacitances will be there, right? So they will also take part in affecting the frequency response, right? So I hope now you understand what is the internal capacitance of a transistor. See, in interview, question can be asked. So what do you mean by internal capacitance? Have you connected any capacitor inside this transistor? No, we have not connected any capacitor inside this transistor, but due to the property of a junction of P and N material, automatically a capacitance will be created, and this is the internal capacitance. Okay, so what is the effect of this internal capacitance on the frequency response curve? That we will see in next class. Okay, right.